In this talk, we'll be discussing our results on the usage of constraint programming to solve differential cryptanalysis problems. So let's start by a bit of context. For instance, we're interested in ciphers like AES, and AES is used pretty much everywhere, including by you right now by watching this video. And we want to make sure AES is actually secure. And we do that by trying to break it. If we succeed, we change AES. If we don't, we may keep it for a few years. One of the very famous techniques people used is called the related key differential attack. This technique is quite interesting because in order to have good attacks, we have to solve some very challenging combinatorial optimization problem. And a lot of people tried different approaches. The most used ones were at some point branch and bounds or dynamic programming. Later, people came with some very efficient CP models, and in the last years, people introduced even more complex CP models that achieved very good performance. However, such models can be quite difficult to generate because it requires a lot of skills. You have to be familiar with symmetric cryptography, and you have to be familiar with constraint programming. It also takes time, and usually people can expect to spend at least a few months to design only one model. These models can also contain bugs, and the solution you get, the optimal solution you get, may not necessarily be optimal. What we would like to do in a perfect world as AI researchers is to define our problem, so our cipher, in some kind of unified modeling language, push a button, and obtain the mini-zinc models for free. All the advanced models for free. And the question we ask in this paper is, can we design such a button?